Hey everyone! In this video I'm going to walk you through a sample collisions problem in which I show you kind of how to use conservation of momentum to be able to predict the motion of an object after it collides or otherwise interacts with another object. Okay, so in this problem, here's our setup. We've got a 3 kilogram object and a 2 kilogram object. The 3 kilogram object is moving to the left at 6 meters per second. It then collides with a 2 kilogram object that's moving to the right at 4 meters per second. After our collision, we still have our same two objects. The 3 kilogram object's now moving right at 2 meters per second, and we're trying to figure out what the 2 kilogram object is going to do. And we'll go ahead and assume that this is a closed system as well, so no outside forces interfering with this interaction or interfering with the motion of our objects here. Okay, so what I've started with, and what I always recommend starting with in these problems, because there tend to be a lot of moving pieces, is drawing a picture. I'm going to draw a picture with all of my objects before their interaction, and I'm going to draw a picture of all of my objects after their interaction. And when I say interaction, that could be a collision or that could be an explosion, whatever the big event in our story is. We want a before and after snapshot of everything that is going on. So I've gone ahead and done that, drawn in my objects along with their masses, how fast they're moving, which direction they're moving, etc., for both before and after that collision, based on all the information that's given to me. The other thing that I'm going to recommend doing right now is bear in mind that momentum is a vector, which means direction matters to us as we are solving these problems. So it's going to be really important for us to keep track of which direction do we consider to be the positive direction, which direction do we consider to be the negative direction. So I'm going to go ahead and stick with moving to the right is positive, moving to the left is negative, which is kind of what I generally do by convention anyway, but just to make sure that I'm very consistent with that, I'll go ahead and write that for myself right here. All right, so I have all this information about all my objects before and after collision. I have a sense of how to make sense and how to keep track of direction in all of this. What I'm going to do at this point is go ahead and just sort of list everything out as well for myself using kind of that guess method. So here's my first object, my 2 kilogram object. It has a mass of 2 kilograms, so I'll go ahead and label that M1 is 2 kilograms. And it's moving at 4 meters per second to the right, which is my positive direction. So I'll go ahead and say V1I. 1 being that this is the velocity of object 1, I being that it's its initial velocity, is 4 meters per second. All right. Now, given that information, since ultimately the thing that remains constant for us before and after collisions, explosions, whatever, in a closed system is momentum. Momentum is our star player in these sorts of interactions. As long as the system is closed, momentum is going to stay the same. So I'm going to go ahead and calculate the momentum of this object as well. So its initial momentum, bearing in mind the fact that momentum is equal to, here, I'll just write this over here. Momentum is equal to mass times velocity. That's going to be really important right there. All right, so I'm going to multiply the mass times the initial velocity for my first object. So my momentum of my first object initially is going to be 2 times 4, which is equal to, that's a times, is equal to 8 kilogram meters per second. Okay, so that is the amount of momentum that the 2 kilogram object contributes to the system before the collision. I'll go ahead and repeat that with my second object here as well. So for my second object, mass is 3 kilograms, and the initial velocity, so V2I, 2 because it's our second object, I because it is the initial velocity, is 6 meters per second, but hold the phone here. I see that the 6 meters per second is going to the left, which I've defined as my negative direction, so I'm going to go ahead and label that negative 6 meters per second for that. All right, so then I'll go ahead and do the same thing. I will calculate the initial momentum of my second object here by multiplying those two together. So that's going to be 3 times negative 6, which is going to be negative 18 kilogram meters per second of momentum for my second object. All right, so I've got all of that information there for me. And I can go ahead and just kind of list out that same information over here. So my first object still has a mass of 2 kilograms, but now I'm trying to solve for its final velocity. I don't know what that is, so I'm just going to leave that as a mystery. All right, and then for my second object, still has a mass of 3 kilograms. Its final velocity, so I'll label that as V2F for the final velocity of my second object, is 2 meters per second to the right. So then to find its final velocity after the collision, I just multiply those together, which gives me 6 kilogram meters per second of momentum there. All right. Now again, we know that in any closed system, the total momentum remains constant, which means that all the momenta here before the collision for my system is equal to the total momentum after the collision. So now I'm going to go ahead and figure out what that total momentum is on each side of this, this event. So then my total initial momentum here, and I'll just go ahead and add the momentums of each of my objects. So I've got 8, and then negative 18, which gives me a total combined momentum for my system of negative 10 kilogram meters per second before that collision. All right, so that's total amount here, means 10 kilogram meters per second of momentum to the left. Let's go ahead and repeat that same process over here on the right. So the total final momentum of my system is going to be equal to, first of all, the momentum of this, which I don't know yet, but I do know that whatever the final momentum of my first object is, it's just going to be equal to the mass times the final velocity. So that's just going to be 2 times final velocity of my first object. Okay, so for now I'll go ahead and use that as my placeholder, and eventually I'll be able to go in and solve that using the magic of algebra. So that's going to be 2 times final velocity of my first object plus the 6 kilogram meters per second that the second object is providing for me. All right, so I've got all of that. These two sums have to be equal to each other. All right, so I'm going to go ahead and move this up here so I have a little bit more space on screen for us. So those two are equal to each other. So that means negative 10 kilogram meters per second is equal to 2 times the final velocity of my first object plus 6 kilogram meters per second. So now I just do a little bit of algebra magic to solve for that final velocity. Right now I see that this final velocity is being multiplied by 2, added to 6. I want to undo those operations in reverse PEMDAS order. So I'm going to subtract 6 from both sides. And here's where we see the importance of keeping track of direction and making sure that anything in the negative direction is negative. It's a big difference from for taking negative 10 minus 6 versus positive 10 minus 6. So we really want to be careful about that. So we've got then negative 10 minus 6 gives me negative 16 kilogram meters per second over here is equal to 2 times the final velocity of my first object. Divide both sides of the equation by 2. And then I'm going to be left then with, give myself a little bit more space here, a final velocity for my first object of negative 8 meters per second, or in other words, 8 meters per second to the left. And that's it. So there are a lot of moving pieces, a lot of individual momentum calculations along the way, but as long as you can kind of stay organized with all of this, consistent with your notation and with your directions, then really it's just a matter of doing P equals MV over and over again and adding things up. And that's all. All right, hope that helps. Thank you.